fun exercise here. So you have this particular contour integral, and the question is to calculate it in two different ways. One of them based on Cauchy's formula, and the other time you calculate it based on parametrization. And then by identifying the two different solutions, try and prove this particular equation over here, which I think would be very difficult to prove otherwise. So pause the video and sink your teeth in this problem. Let's first do Cauchy's formula. So Cauchy's formula, as a quick reminder, is that if you have a holomorphic function f of z, that then the integral of f of z divided by z minus z naught dz is equal to 2 pi j function evaluated in that point z naught. Now here our integral is the following: e to the power of az divided by z dz, where obviously for f of z this time we have exponential az, and for the point z naught that just becomes the origin. So if we apply Cauchy's formula, that gives us 2 pi j, and then f at the origin, so that becomes e to the power of a0. So that's just 2 pi j. Okay, so we know the end result. We know what the value of that contour integral is. Let's now try and express that same contour integral, but using parametrization. Parametrization of the unit circle, which is z exponential j theta, with theta running from 0 to 2 pi. So if we do that, we can write that the end result of our integral, which we have calculated to be 2 pi j, right? So 2 pi j is also equal to the integral from 0 to 2 pi. So let's write it a little bit lower here. So 2 pi j is the integral from 0 to 2 pi of e to the az. So this becomes e to the power of a, and then z being e exponential j theta. Let's apply Euler here and write that as an expression involving sines and cosines, because this is basically what we're working towards. So this becomes cosine theta plus j sine of theta for z. And then we divide that by z exponential j theta, and then we have dz. So we just take the derivative here of that expression, giving us j exponential j theta d theta. Good news is that this exponential j theta cancels. Another thing that cancels is the j here in the left-hand side and the right-hand side. So if we summarize this, we have shown so far that the integral from 0 to 2 pi of e to the power of a cosine theta plus j sine of theta d theta is equal to 2 pi. Okay, let's massage this expression a bit more. So first of all, we can write this as e to the power of a cosine theta times e to the power of a j sine theta d theta. And then we can apply Euler once more to the second factor. So 0 2 pi e a cosine theta. And then we have e to the power of j something. So this becomes cosine of that something plus j sine of that something. So this becomes cosine of a sine theta plus j the sine of a sine theta d theta is equal to 2 pi. Okay, what we're now going to do is we're going to take the real part of that expression that will allow us to get rid of this sign here, because what we're working towards is an expression that involves the cosine over here. So if we take the real part, we end up with the fact that the integral excuse me, from 0 to 2 pi of EA cosine theta times cosine A sine theta d theta is equal to 2 pi. And by the way, at this point, it would also be quite trivial to prove that a similar integral here, having a sine as opposed to a cosine, will be equal to 0, simply by taking the imaginary part of that expression over here. Now we're almost done. The only thing we need to do is work a little bit on these integration bounds here, which are now from 0 to 2 pi. But we can also rewrite that as an integral from minus pi to pi, simply because our function is periodic in theta. So theta appears here inside the sine and there inside the cosine. Both of these functions have a period of 2 pi, so we can just shift the integration to go from minus pi to pi. What we're really interested in is an integral from 0 to pi, so only half of that integration domain. And the question is, what happens if we replace theta by minus theta here in the integrand? So let's first have a look here. Inside the cosine, if we replace theta by minus theta, nothing will change. Cosine is even. Here, on the other hand, we have it inside the sine originally. So this is not an even function, so there will be a minus sign appearing here. But luckily, it's again inside another cosine, which will annihilate the minus sign, so to speak. So we can conclude that the whole integrand over here is an even function. So therefore, the integral from minus pi to pi is 2 times the integral from 0 to pi. And that's exactly what we needed to show, namely that the integral from 0 to pi EA cosine theta cosine A sine theta d theta is equal to pi.